Hey guys, how's it going? I just made a quick little video here to explain the next part of our translating unit. We got a little practice last week talking about how to translate a point around a coordinate plane. Here's an example of one. Like we're going to take a point labeled A. It's at a location at -2, 3 on a coordinate plane. We want to translate it 3 units up and 5 units to the left. Okay, I asked you to draw some vectors when you do that so that we can build a concept, so we can see a geometric relationship here. Because we want to ask the question now, how far did A translate once we take this point and translate it this direction here? Okay, so I'm going to show you real quick this example. A, we said from the problem, is going to translate 3 units up and 5 units to the left. So I'm going to take A here and I'm going to go 3 units up, and then I'm going to go 5 units to the left. And A prime, the translated point, A is going to translate to A prime at this location here. Okay? So now the question is, how far did A actually translate? What's the distance between A and A prime? The other way of looking at it is, what's the length of this vector? Right? Those are all the same question. Alright, so we need to figure out how we can find that length, and the directions of how A actually translates the up and the left movement actually create a nice geometric figure here. So I'm going to take A and I'm going to show the vector of it moving up 3, and then I'm going to show the vector of A translating 5 units to the left. Okay, so I'm going to grab my pen tool here. The length of this vector, the distance between these points, is that movement of 3 units up. The length of this vector and the distance between these 2 points, and the movement now, the movement here is a -5, right? If we think about direction, the sign gives us direction. Negative means moving to the left. But if we want the distance, which is always a positive value, or the length of this vector, which is always a positive value, we actually want to take the absolute value of all of our sides, which will guarantee us then that we always get out a positive length, because all we really care about is the distance between the points. And direction doesn't mean anything when we talk distance. Okay, so just think absolute value so that we can always make our movement a positive, which is really the length of this vector, or the distance the point moves. Okay? Alright, so now we know that horizontal and vertical segments are always perpendicular to each other. So when we translate a point using a vertical and a horizontal movement, it's always going to create some kind of right triangle. Okay? We'll always know 2 of the 3 sides of our right triangle as well. So we can use Pythagorean's theorem then to find the length of the 3rd side of the right triangle, which is really the vector that shows the translation of A as it translated 3 units up and 5 units to the left, right? So we can find that length. So a quick little refresher on Pythagorean's theorem. Alright, so here's this GeoGebra app that we used earlier in the year. Right? Pythagorean's theorem says that the area, so we have a right triangle, by the way, right? So here's an example of a right triangle. Okay? A squared plus B squared equals C squared, the famous Pythagorean theorem. Now remember the concept behind A squared. A, B, and C are sides of the triangle. A and B are the legs, right, the shorter sides. C is always the hypotenuse, which is the hypotenuse is always the largest side. It's across from our 90-degree angle. Pythagorean's theorem says this: if you were to make squares based off of the side length, right, hence A squared, make a square out of it, and find its area, which is length times width, and if since this is a square, if, for example, I'll get my pen tool again, if this side is 4, which it is, and this side is 4, then the area is length times width, or 4 times 4, 4 squared. We get an area of 16. Okay, this other side here also has a length of 4, right? So then the area of this square will be 4 squared. So the area then is 16 for this square as well, right? So the area of this larger square is going to equal the sum of the areas of the 2 smaller ones. So if we add these 2 areas together, we know then that the area of this square is going to be 32, And our connection to squaring a number and then getting back to the side length is always going to be the square root of the area. So in this case, when we look at the square root of our area, 32 is not a perfect square, so our exact length is going to be the square root of the area, square root of 32 in this case. And if we were to get the decimal of it, we could just put this in our calculator and approximate about what this length is. And so GeoGebra did that. It actually is about 5.7. Okay, and that's 5.7. So then we know that in this example here, we would have a hypotenuse that is 5.7 about, or exactly the square root of 32. Okay. So that is an example of Pythagorean's theorem. Okay, just remember what that means. So let's apply that to our picture here. Okay, so I'm going to get rid of my pen stroke. We know that this length is 5, this length is 3. So if I were to make a square based off of the length 3 here, then we have a square that is a 3 by 3 that has an area of 9, right? So that's the area of this square. If I find the area of the other smaller square here, so this is 5, so if I go up 5 more, right, and make a square that's a 5 by 5, the area of this square is 25, right? 5 squared plus 3 squared, these two areas added together, must equal the area of the larger square here based off of our hypotenuse length, that vector that we want to find. Okay, so the area of the square we know is going to be the sum of our two areas, the 25 plus the 9. Okay, so in this case, the area of this square is going to be 34 units squared. Therefore, the side of the square is automatically the square root of 34. Okay, 34 is not a perfect square, so this is an irrational number. So let's just keep our answers exact. Let's get used to writing our irrational numbers as an exact value, which is this interpretation. So the question, if A translates 3 units up, 5 units to the left, how far did it translate? Well, it translated exactly the square root of 34, right? So if we want to get an idea of what that is about, okay, then we can use our calculator and we can find out what that is. So I'm going to grab my calculator and I'm going to take 34 and find out what the square root of it is, which is right here. So really, if you look at this length as a decimal, it's about 5.83 units long. That's about how far this point translated. Okay, so that's how we use Pythagorean theorem to find the length of a vector that is diagonal by using the vertical and the horizontal components of that diagonal length and using Pythagorean's theorem. So your assignment then is to take this worksheet. I have Pythagorean's theorem on there for you. I am showing the absolute value because we always want these distances to be positive. So if it's a negative movement, the distance is still the positive length. So that's what the absolute values are showing. And then you have 10 problems on translating points and then also finding out how far a triangle, a figure, had slid. Okay, so you got 10 problems with that. So good luck with all that, guys, and I'll see you tomorrow.